vibration. And we touch also on the types of vibration system, which is free vibration, force vibration, undamped and damped vibration. So we define all this during our previous class. In fact, we also touch a bit on the different classification of vibration, which is linear and non-linear vibration, deterministic and random vibration. I do remember there's one of you asked about the heart rate, whether it is deterministic and random vibration. In fact, I would previously, if I'm not mistaken, I would say the heart rate is a random vibration. Actually, it can be both. It can be deterministic and also it can be random. So when does this heart rate become deterministic, which is a normal heart rate, a normal people heart rate, but random vibration could happen when a person who have heart failure, where the heart rate is not pumping in a in it is how it's supposed to pump. So the vibration given would be a random vibration rather than deterministic. So both this heart rate can be both. And beside that, I also introduced to you what is single degree of freedom, where we have normally single degree of freedom, we have one mass. And then I also introduced to you what is 2 degree of freedom system with 2 masses. Okay, 3 degree of freedom, 3 masses. And we also looking at the what we call example of the mathematical model of the motorcycle, which shows the combination of the spring and also damper in the system itself, right? So today I'm going to touch on this system element, which is consider can someone of right all right, which consider the what we call this what we have in the system itself, system elements, before we go deep into how we going to derive the 1 degree of freedom, 2 degree of freedom for the vibration system. So we look into this system element first. Okay, generally this one I have introduced before. The schematic of the linear system can be shown in this figure here, where there's an input and there is output. Input xt, so the output will be yt. So the linear system the system will be linear if it is fulfilled this. For example, x1t, the output is y1t, x2t, y2t. Then when we combine these two input here, x1t plus x2t, it will give output of y1t plus y2t, right? So this equation, actually, the governing of the equation just now, the linear system equation just now, is a differential equation, right? Okay, differential equation, I think you probably familiar with this differential equation. You have come across this in your maths class, where we have, let's say, an power d power of ny over d okay, plus we have a1 dy over dt, so here plus plus a naught y equal to dm dm over dtm. So this is supposed to be dx, dmx, dt power of m, right, plus b1 dx over dt plus a naught x. So this is general differential equation. If you notice here, this we call this equation is referred to an order differential equation. So in mechanics, the differential equation usually represent force equilibrium, and each correspond to some kind of this physical force, and the force are in the balance. So y here is the output, and x as y is the output, x is the input. So it depends what is the order of the equation here. Okay, uh, for the okay for the special case, a second order system. The second order system is the most common system that we use in vibration. So what does it mean by the second order system? Second order system is powered by two. Right? So it represents a balance between the applied force and the forces arising from the inertia, or we call it the acceleration, the damping from the velocity, and the stiffness from the displacement. So normally we write this second order. I think this you also familiar with this. An, this one, d y double dot plus a1y dot plus a naught y equal to a naught x. So this one is a common in a vibration system. So this y here is the output, x here is the input, right? And y double dot here represent the acceleration, y dot is represent the damping of velocity, and y displacement come from the stiffness, right? Stiffness of the spring, right? Placement from the spring. Okay. Now let's look at some of the example for the system using that we can represent using the second order. The first one is mechanical system. So the mechanical system here, as you can see here, this is a car suspension system. So we can represent this car suspension system in the form of the second order differential equation, second order system. The second one is electrical. This electrical here is the audio amplifier response. So this is how it responds. This one also we can make a mathematical modeling using the second order. The second order. The third one is thermal. Example for thermal is the heating and the cooling of the building, heater and also the air conditioner here. Okay, these two also can be represented in the form of the second order system. Okay, now let's have a look at the system elements in detail. Okay, so for mechanical system, there are two different type of the system element. The first one is the translational motion. The second one is the rotational motion. Okay. Right. Okay. Each of these have three main elements. Okay, which is for the translational motion, mass, a spring, and damper. For rotational motion, torque, torsional spring, and torsional damper. Let's have a look at the element one by one. Okay, for the translational motion, the mass here, okay, let's define first. If let's say we have mass here, m, so giving a force, dy, y dot, and y double dot. So the force, okay, from this mass here, we can get by F equal to m y double dot, okay, or ma squared, the acceleration. Ma, or mx double dot also. Since this one using y, so my double dot. So how much work produced from this mass? So work equal to integration of force here. The force here. So my double dot. Sorry, dy. So if we want to integrate this, we can simplify. So y double dot can be dv over v is velocity, dy, multiplied by dy, right? So from here, if we cancel this, okay, then we can get half m v squared. So who can relate? What equation is this? So what equation is this? Anyone?
Velocity
Yes.
dengan acceleration.
Kinetic, I heard someone mention kinetic energy. Yes, it is a kinetic energy. So I can say that the mass here, okay, mass transmit the energy which possesses by this kinetic energy here, Ke, okay, we call this one is kinetic energy, Ke equal to half mv squared. That is for mass. Second one, spring. Okay, how we define the spring, force in the spring. Okay, let's say we have a spring here. And we push this spring, right? So meaning there is a displacement, y displacement here, and we have the constant spring K here. So force here equal to F equal to K, 1. So what is the work done by the spring here? Work done here, we can integrate the force F d y equal to F here is ky dy. So when we differentiate this, we can get half ky squared. Okay. If this is x, then x, right? A half kx squared. So since I put displacement here as y, so half ky squared. So anyone, what equation is this? Anyone can relate? What equation is this? This is the equation for spring, right? So this half kx squared is the potential energy equation, PE, potential energy. So here spring store energy, okay, half a y squared. So spring store energy, right? So next one, damper. Okay, let's define first damper. I usually use symbol for the damper. Let's see this damper. We put a force here, F, and also so there should be, let's see here, there is a displacement velocity here, so acceleration, right? So the force, obtained from this damper would be F equal to, let's say, the what I call the constant for damper, it can be COP. Okay, I might use it interchange. I might use either of the COP. So this is the constant for damper. So here F equal to C Y dot, right? So the work done, okay, the work done by the damper would be work equal to the integration of the force, just force here. So Cy dot Gy, sorry, Cy dot, so this one, okay, we can put it, we can define it also as y dot dt. So y dot dt here is equivalent to dy here. So from here, if let's say we integrate cy dot squared dt, so what do we get here? We get cy dot cy dot, is correct or not? Cy dot squared, right? Cy dot squared. Okay, so this cy dot squared is a what you call, since the speed in the system is not consistent, so the energy produced by damper would be varies as well. So the power dissipated, okay, normally the damper will produce the power, the dissipated energy to the system, right? Okay, that is for translational motion. Now let's have a look at the rotational motion, torque. So actually torque also we can define as what we did just now, but I just show to you what is the general torque equation, right? For T here, for torque here, okay, the kinetic energy for torque here would be KE equal to, sorry, torque first, the torque equal to J theta dot T. You are familiar with this, right? This is the general equation for torque T. So the kinetic energy, so actually you can check by yourself, okay, by defining how I define the translational motion just now. So KE here would be half J theta dot squared, or you can write it as half J omega squared. This omega here is the angular velocity. Okay, angular velocity. Remember, this inertia is due to the rotational motion. So of course the velocity also in the angular, in the rotational motion as well, right? So that's for torque. Torsional spring. Torque for the torsional spring here. Okay, sorry, this one is rotational motion here. This is not torque. It should be inertia. Inertia is from the mass, from the mass itself, or inertia. Inertia, the torque value here is T equal to J theta, right? Okay, for the torsional spring here, the torque produced by the torsional spring would be T equal to K theta. So how much displacement measured in a rotational. which is theta. So the torque produced by the spring would be T equal to K theta. So if you want to find what is the potential energy from this, what I call the torsional spring here, then you have to define as what I did before. But I put the general equation here. So potential energy for the torsional spring here would be half K theta squared. Okay. So remember, this is angular displacement. Angular displacement. Next one, a torsional damper. So torsional damper, let's say you have, okay, this is the spring here. This is how it looks like. I think you learned this in your AMM, analysis of mechanic and machine. So this is the symbol. Okay, let's say the spring here have the constant KT, and then we have the displacement theta here. So this is the torque given by this spring here. Okay, next one is torsional damper. Okay, if let's say we have a damper, I just put a symbol like this. Okay, damper. Oh, okay, theta, and we have the CT is a CT or BT. This is a constant for the damper itself. Theta here is the displacement value, okay, for the system itself. So the torque here governed by this damper would be CT theta. So the work done or the power dissipated by this damper, right, would be equal to C theta dot square. Okay. All right. So from all this definition here, we can actually conclude that there are three main principles. Okay, there are three main principles here, which is the first one is the conservation of energy. Conservation of energy, which where is the total energy of the isolated system remain constant. It is said to be conserved over time. All right. And then the second principle would be the conservation of the linear momentum. So the conservation of the linear momentum, whereby the total momentum of the system is always conserved if there is no external force acts on the system itself. The third principle would be conservation of the angular momentum. So these two is the same: conservation of the linear momentum, conservation of the angular momentum. So for the third one, when no external torque acts on the object, so no change of the angular momentum will occur. All right. Okay. So just now we have looked into the mechanical system. So now let's have a look to the analogous of the electrical system with the mechanical system, on the principle of what you call the main three principle just now, which actually related to the what call the energy transmission of the energy, the dissipative energy, and also the energy that as the element that store energy. So there are three main elements here, which is the first one is inductance, the second one is the resistance, and the third one is the capacitance. So inductance here, okay, if you still remember, okay, you learned in electrical EET last time, electrical engineering technology. So this inductance here, okay, the voltage given by this inductance here would be V equal to L di over dt. So if we define the energy from here, it will be E equal to half L, sorry, Li squared. So I here is a current, L is the inductance value, right? For resistance, okay, you know that V equal to IR. I hope everyone still remember this. So the power obtained from the resistance here will be I squared R. Okay. For the capacitance, I equal to C. C is for the constant for the capacitance here. C dV over dt. Differentiation of the voltage over time. So if we integrate this, okay, we can get the energy from the capacitor would be half CV squared. Okay, if we look into these three elements here, the first one here, E equal to half Li squared. So this actually similar to the similar to the mass in the mechanical system where it can transmit energy. The second one here, P equal to I squared R. This is similar to the damper where where the resistor here will dissipate the energy. The third one here, the capacitance, okay, E equal to half CV squared, which is very similar to the spring, where it can store energy. So this is the analogous of electrical system with the mechanical system. This is spring. So mass, inductance, damper with the resistor, spring with the capacitor. Sorry, this one. Okay, this one. Sorry. Okay, so now we have defined all the what you call the energy for the main elements in the system. Okay, so let's have a look at the specifically first one to the spring. Okay, how we going to calculate the value of spring? Okay, if we have a spring in the parallel in the series, and how does the potential energy of the spring will be calculated if let's say we have various spring in one system. The first one is the linear spring here. Okay, the first one, linear spring. Linear spring, we have the parallel combination of spring. For the parallel combination of spring, okay, how do we find the total constant value here for the spring? So this spring is in a parallel. So actually the KE for this system here would be equal to summation of KI from I equal to 1 until N, right? So if let's say you have N spring connected in a parallel, meaning you have to add all the spring constant here until N. K1 plus K2 plus until Kn. So since we have two spring here, so the total constant for the spring here would be K1 plus K2. So we can simplify this. Here we can simplify this system into this. Okay, so let's say we have force here. So the value here would be equal to Ke, right? Combination of these two. Okay, how about the potential energy for the spring itself? Okay, potential energy, PE. So the potential energy would be V1x plus V2 X. So you just combine the potential energy for each of the spring. So let's say for the first one, we have half K1X squared. The second one, we have half K2X squared, right? Or we can simplify K1 plus K2 X squared. So if let's say you have combined it into KE, you can simplify some more half KE X squared. So for the parallel combination spring, then you can do this, okay, for the potential energy of the spring itself. Okay, for the torsional spring, let's say this torsional spring, the torsional springs are arranged in the parallel. Okay, let's say, okay, let me draw it. Okay, this one meaning to say that we lock it here because it is caught in parallel. So meaning to say that it should have like, this is the first spring. Okay, let's start. So it was locked there, the first spring, and it will combine with the second spring. So this is the second spring, and we lock it here, right? So when we exert a force in the spring here, so what happened is that one spring will exert in X value, the other spring will compress the X value. So the X, okay, one spring will exert, where if we have a force here, okay, one spring will exert X value, sorry, yeah. The other spring, the first spring will exert, the second spring also, the second spring will compress, also X value, okay. One exert, one compress. So both spring experience the same X value movement. So experience the X value movement. So how does we define the potential energy? Still the same. So we have, let's say, potential energy for this torsional spring. We put it as torsional is T. So we put Vt X equal to Vt1 X plus Vt2 X. So equal to half Kt1 theta squared plus half Kt2 theta squared. So these two springs have the constant value K1, different constant value, K1 and K2. So K1 and K2. So you can always simplify this, right? Half Kt1 plus Kt2 theta squared. Or if let's say you have simplified this, okay, this is in parallel, so your Ke also equivalent to the addition of this. Same goes to the linear spring just now. So it would be K1 plus K2. Sorry. Okay, so here would be equal to half K T E theta squared. So in general, this spring, let's say we have the torsional spring and torsional spring put in a parallel, then we have KTE equal to summation of KT I from I equal to 1 into n. So this is general. if you look into the system, there's no, when you add this constant value, it is the same with the linear spring. Okay. So how about the spring, linear spring in the series combination? Okay. So for the spring in the linear spring in the series combination, there should be two spring here. Let's say I put it here as K1, here is K2. So you imagine there is two spring here, which is connected with each other, K1 and K2. So what is the KE value here? What is the KE value here? So this KE value for the linear spring in the series would be 1 over KE equal to 1 over K1 plus 1 over K2. So KE would be equal to K1, K1, K2. K1, K2 over K1 plus K2. This is only for two spring. If three spring, then you have to combine it. Okay, you have to plus here and then you have to find what is the value for this KE. So in general, we can say that the kinetic energy for the linear spring in series will be equal to summation of 1, okay, summation of 1 over Ki from I equal to N, I equal to 1 until N, but you have to inverse it, okay? Then only you can get the KE value. So potential energy for this linear spring in the series combination is still the same. Okay, we have Vx equal to V1x plus V2x equal to half K1x 1 squared plus half K2x 2 squared. But if you want to combine these two, then you have to find this first. Then only you can combine these two. If not, then you can leave in this form. Right? Okay, that is for the linear spring. How about for the torsional spring series, where we put it in series? Okay, the rule also the same with the linear spring just now. So we have only, we lock this here. So this is the first spring, and this second spring started from here. Okay, and let's say we have force given here. How to make it? Let's say we have top, no force, top given here, T. So of course over here also the same value given in the same direction. Okay, this is the first spring. Okay, then this is the second spring. So we exert same torque here. Okay. So the end spring in series for the torsional spring also the same with the linear spring just now, where your KE would be equal to I equal to 1 until N, 1 over Ki, and you have to inverse it. So for the case over here, I would say 1 over Ke will be equal to 1 over K1 plus 1 over K2 equal to K1, K2 over K1 plus K2. Right. That for the torsional spring. Okay, up to here, any question before I continue with the common structural elements? Any question? Yes, no? No, madam. All right. Okay, let's continue. Okay, just now we have seen the, we can see the general, what we call, general type of the spring. I think you might have come across before. So if you look at this slide here, if you still remember, I've shown this to you before, how we can simplify the structure here into equivalent spring and mass system. So any elastic or deformable member or element can be considered as spring as well. So over here, okay, this, we can consider this structure here can be considered as a spring because it is deformable. So the elements here deformable. It can swing. So that's why we can simplify the system here, even though this system is actually the nonlinear system, but we can simplify into a linear system by uh, by simplify the model into the spring and mass. But of course, the value of K for the structure here would be different, right? Depends on the structure itself. Okay, for example, here the first one, we have what we have here. We have road. Okay, we have road here. Okay, so this road actually can be simplified into a simple spring as shown in the slide here, right? So let me have a look first. Okay. So this is the delta value here. Okay, we have the length of the road, and if let's say we exert a force on this road here, then we can get what is the energy, okay, obtained from this. So how does we define this K here? K AE over L. So the elongation delta here is considered the elongation here, delta, right? I think you learned this before, okay? The elongation here would be equal to epsilon L, right? Epsilon L. So equivalent to also the sigma over epsilon, big epsilon, yeah, or E. What you call the sigma over E multiplied by L, right? So here, this is E here is the Young modulus, right? This is the Young modulus. So the K for a system should be the force applied over the resulting deflection. Okay, so which give you F over delta. If you look here, F equal to delta, K delta would be F equal to Kx, sama? Same, F equal delta X, so equivalent to here, AE over L. Oh, sorry, this one I haven't finished. This one equal to F L over A. So from here, then you can get AE over L. This is for road. Okay. Next one, another example would be the cantilever beam. So for the cantilever beam here, you can see the beam here is fixed at one end, but on the other hand, on the other end, there is a mass attached to it. So when we push this cantilever beam downward here, then this beam actually acts as a deformable member of elements. So here we can simplify the system into a spring and mass system. So K here for the cantilever beam would be K equal to 3EI over L cube. Okay. So this one also there's a way to define it. You can find you can try to find how to define this thing, but normally this value given in the exam. So this is other example of the elastic and deformable element here. You can see axially loaded rod or cable. So how does it look like? This is the same that with the first example given just now, which is K equal to AE over L. Axially loaded tapered rod. The rod is tapered, so a bit different here. So this is the K value. The hollow circular rod in torsion. This is in torsion, different. Torsion, this is rod, torsion, this is rod, axially exerted. Okay, linearly exerted. So the value here equal to K equal to GI over L. So G here is the inertia, I is the moment of inertia, I here. Different from here. A here is the area, E is the Young modulus, and over L. Right? Different. Cantilever beam, this one the same with the example just now, 3EL over A cube. Then we have different structure, which is pin beam, given different value of K, clamp beam. Clamp mean fixed to at two ends here. Okay, this one only pin. Two circular rod in torsion. Okay, this one attached together. So the value would be this. You can see the example here. The value of KTE here would be okay. Okay, the addition here, we call the equation that I have defined just now. All right. So this one is this rod is attached in a series. So this is how you define the KTE. All right. And two circular rod in torsion. Two circular rods. Is it the same? Yeah, this is the two circular rod in torsion. Okay. Okay, that is for the elastic and deformable element. All right, we have seen the spring and spring in general, how we define for the parallel and also series combination. We also have go through the what we call the elastic and deformable elements, which can be analogous to the spring itself, okay, which is rod, cantilever beam, yeah, and so on. So now let's have a look at this damper. So how does we calculate the the constant for the damper if we combine it in a parallel and also in a series? So for the damper here, let's say we put the damper in a parallel. And we exert a force like this. Okay. So this is damper. We have C1 constant, the first one, and C2. So what is the value for the combination of these two damper? So this is in parallel, right? So this damper, the addition of damper would be CE equal to C1 plus C2, right? E, A. How about the series combination damper? Okay, let's say we have a series combination of damper. first damper, the second damper in series, and we have force exert here. They say this one C1 and C2. The combination of the series would be 1 over CE equal to 1 over C1 plus 1 over C2. C1, C2 over C1 plus C2. So you can simplify into this form. C A. I think this one is pretty straightforward because we have defined for the spring before this, right? So this is for damper. If you encounter the damper in the series and in parallel, you can combine those damper using the general equation here, right? Okay, I think I'm done with damper. Now let's have a look at the example here. Okay, let's say consider this figure here, then we try to suggest what is the equivalent spring model for the system here. If you notice here, for the first example here, we have K1, we have K2, K3, and K4. Okay, I think this figure should have, this one is attached. This is fixed. Okay, this spring fixed. So we have this, and we attach to the mass. So how do we combine the system here? All right. Okay. These two in series. So we know that this, let's say we put here as Ka equal to 1 over K2 plus 1 over K3. So equal to K2, K3 over K2 plus K3. So now we have Ka here. If we simplify this Ka and K1 here would be in parallel, right? So when we have this, meaning that we have simplified the system into this. This is M, this is K1, Ke, and here is K4. So these two in parallel, so Kb will be equal to Ke plus K1. Sorry, no Ka. This is Ka. Ka plus K1. Because this is in parallel. So now we have simplified into this. Okay. M fixed to N here, right? So we have here Kb is all right, and we have here K4. So how do we simplify this? If you imagine this one as one node, okay, and the force is given at the node here, okay. They say force given here, one node, so this will follow. So actually, these two spring is in parallel, which is each other. Okay, these two spring would be in parallel, which is with each other. So you can imagine it in this way. Okay, this is Kb. Okay, imagine this node is the mass. So this is K4. Okay, this is fixed. This is fixed. Then there is a force here. So this actually sitting in a parallel. So your final the equivalence the equivalent constant for the spring in this system will be Ke equal to Kb plus K4. right? So that is for the first example. Okay, the second example here, I think this is pretty straightforward. We have two springs connected to mesh here. So two springs connected in parallel. So your KE will be equal to K1 plus K2. Okay. The third one, okay, we have the deformable structure here. All right. So deformable structure here. Okay, so this one is act as a spring as well, right? So now when we have a force here, so this is the connected spring here. So we have a spring connected to this point and connected to this spring connected to the second spring here, and we have force given here. So actually you can put this in this form. This is the structure, spring, deformable structure, and the first one combined with the second one, or we can put in this way. Okay, this is the free spring from this structure here. This is the point here. Okay, the second one. So we have mass and we have exerted force here. So we have here, they say here is KE and here is K. So since this is in series, so you have to inverse, right? So 1 over KE would be equal to 1 over, so 1 over K plus, sorry, this is, sorry, this shouldn't be KE here. They say this one is K2. K2, so 1 over K plus 1 over K2. But this one you have to find first what is the K here, okay, using the equation given in the table just now, right? If this is a road, we can use the equation EA over L, right? If it is a road, this K would be equal to AE over L. If it is a cantilever beam, then you have to use the cantilever beam equation. All right. Okay, I think that's all. Okay, I think that's all for today. Any question before we stop? And you have 2 exercises to complete before 2 p.m. today. Submit through Ellipse. I have opened the link for you to submit the exercises. Any question before we stop?
Was it before?
Yes, 2 p.m.
Okay.
159 still okay?
1 minute. No, I cannot do it.
Come again?
No. Okay.
Right? Any question? Okay.
Will you upload the introduction notes, Nilip, Doctor?
Yeah, I will upload it after this. Right after this, I will upload it.
Okay.
Okay. If possible, I don't want to have any what you call manual attendance, huh? Unless you have a very strong justification for that, or you haven't. I know some of you haven't registered. Okay, let me open the QR code first before we end the class. Okay, you can log into this QR code here. Okay, those who have logged in, you can leave the class. Thank you very much.
Thank you, Doctor.
Yeah,
Thank you, Doctor.
all right.
Doktor,
Yes.
Doktor, hari ni kan kami ada kelas elektif Operation Research pukul 12. So, Doktor bolehkah kalau extend masa untuk hantar exercise tu?
You still have 1 hour to finish. I think
Okay.
sufficient, right? I
Okay.
think 1 hour is more than 1 minute more than enough.
Okay, it's okay. Thank you, Doktor.
All right.